Raman spectroscopy is an analytical technology used in industry and academic laboratories to understand the structure of molecules and the composition of molecular mixtures in a liquid, slurry, paste, or solid phase. Raman is often compared with IR spectroscopy because both provide information about the structure and properties of molecules from their vibrational transitions. A key difference between Raman and infrared spectroscopy is that Raman is a scattering phenomenon, whereas infrared is an absorption technique. There are two types of scattering, Rayleigh and Raman. Rayleigh is elastic scattered energy, which means the frequency of the scattered photon is the same as the excitation photon frequency. This type of energy is non-informational to the chemical makeup of the molecule being interrogated. Raman scattering, however, is inelastic photon scattering and is highly informational to the chemical makeup. Raman scattering requires two steps to occur for a molecule to Raman scatter. This two-step process is 1. The excitation source photons excite the molecule into a virtual energy state, and 2. The molecule relaxes through a release of scattered photons to a ground state. This effect is rare, with only about 1 in 10 million scattered photons being Raman scattered. Despite the effect being weak, today's technology advancements in solid-state lasers, gratings, and CCD detectors make Raman a valuable tool for identifying and monitoring compounds in a reaction or crystallization. The scattering can be either Stokes-Raman scattering, where scattered photons are at longer frequencies than the excitation photons, or anti-Stokes scattering, where frequencies are shorter than those of the excitation photons. Stokes scattering is the most common type of inelastic Raman scattering that is measured by Raman instruments today. The frequency of the Raman scattered photons is dependent upon the type of bonds, as well as different atom-to-atom bonds, that the laser photons interact with. This specificity of the Raman scattered photon frequency makes it valuable for its ability to identify molecules, acting like the fingerprint of a molecule. The Raman scattering of these different chemical bonds and bond types is represented in a spectrum as a function of the Raman shift versus intensity, with the Raman shift being the shift of the Raman scattered photon frequency from the excitation frequency. The intensity of the Raman signal is directly proportional to the number of a particular chemical bond or bond type. So with calibration, Raman signals can be quantitative. Additionally, when coupling a probe to a Raman system, it is now possible to measure these bonds and their changes in real time. This is valuable to understand reaction characteristics such as kinetics, initiation, endpoint, intermediates, crystal form, molecular backbone, and mechanistic information. For more information, go to mt.com/Raman-spectroscopy.